Thanks for having me. I'm not started yet, right? So, yeah, welcome to my session about what the CRaC, coordinated restore at checkpoint on the Java virtual machine. First about me, just shortly, my name is Gerrit Grunwald. I'm working for Azul Systems as a senior developer advocate, like already mentioned. And at Azul, we do JVMs. So, and if you would like to have the slides, then now is the time to take a snapshot, because then you will find them on SlideShare. You can also go to SlideShare and look for what the CRaC, you will find the slides. It's not the current version because I change it all the time, but they are quite up to date. I have to update them again. All right, so Java is great, right? I think we can all agree. We have a vibrant community, and heads up to this awesome conference. 900 attendees is what I heard, and that's a blast. I mean, we are talking about Voxxed days, right? It's really awesome. And we have hundreds of Java user groups, and we have thousands of free open source software projects. But the real star of the whole ecosystem is the Java virtual machine. I think we can all agree to that. But the question is, how does it work? And usually when I see the audience, because I can't see you now, I ask them, how does it work? And I ask, who knows how it works? And usually nobody points the fingers up, and I bet you all know better than me. But nevertheless, let me give you a very easy introduction. So we start with source code file, some Java file, and then we put that into Java-C, compile it into a class file. That one contains cross-platform bytecode. That means if you have a JVM on your platform, you can run that code. Okay, this is the class files that coming out of Java-C compiler. And then we take this class file that contains the bytecode and use the class loader and then loads this stuff into the JVM memory. It looks easy, it's much more complex, but that's not the thing we would like to focus on. Okay, once it is in the JVM memory, from there it gets into the so-called execution engine. And you see already, the execution engine contains a lot of different parts where we have, for example, the interpreter, the C1 JIT compiler, formerly known as the client compiler, or the C2 JIT compiler, which is formerly known as the server compiler. Then we also have a profiler and a garbage collector. You probably all heard of these things, but maybe don't know how it works. And we will only focus on the first three parts here. And I say formerly known as client and formerly known as server compiler, because before JDK 7, if I'm right, these have been separate things. So usually if you have a desktop application like your IDE, NetBeans, IntelliJ or something, you don't want to wait seconds before the stuff starts up when you double-click the icon, but you would like to double-click, check, should be there. There was a specific compiler for that, that's the client compiler. And the server one was when you run it on a server, and there usually you didn't need really this instant startup, right? It was okay to wait. Okay. That changed, by the way, but we will come to that. So if we take a look now, the interpreter, it takes the bytecode and compiles it into the instruction set of the CPU, and the JVM is watching that and profiling, and it's counting method calls, right? Once a specific amount of calls is reached, it will take this hot code and forward it to the C1 compiler, right? And in the C1 compiler, this is the client compiler. This is just compiling the code very fast without a lot of optimizations. So, and the reason for that is if you run it on the desktop, you really would like to have instant start, right? That's the main reason we don't do a lot of optimizations here. And then again, this compiled code from C1 is running, and again, the JVM is watching that and counting again how often specific parts of the code have been called. And if another threshold is reached, it will take this code and forward it then to the C2 compiler. The C2 compiler is much more complex than the C1, and it takes longer to compile the code, but it does a lot of optimizations to it and creates really good code, or let's say fast code in the end, right? So this whole thing, when we take a look at it from another point of view, that leads me to the execution cycle. And that's in principle the same stuff that we saw before. So we have interpretation first, and you see this execution level. No, there are different there are different execution levels if you come from interpretation to C1 to C2. And this is just the standard. There are different transitions between these interpreted code and C1 compiled code, C2 compiled code. and this is execution level 0 is interpreted code, then this will be profiled, and we try to find hotspots, which is the reason why the hotspot compiler is named hotspot compiler, and then we forward it to C1, we do the compilation, another profiling phase, and then it goes to C2, where it will be further optimized, and then you see this other thing there, and this is so-called de-optimization. Sounds strange, but makes sense. So that happens, for example, I will come to that, but just shortly, that happens if you have optimized code and then maybe something went in a totally different direction than the compiler thought it would, and then it suddenly has to de-optimize the code. So de-optimization. If we take a look at a very simple code block like this, which is just an if-then clause, and it just checks if the value is greater than 0, and then the result equals 3. Otherwise, the result equals 0. So if the profiler figures out, well, most of the times, let's say 99%, the value is always greater than 0. Then instead of doing this whole thing, it just reduces the code to this. It just says, the result equals 0 all the time. But it guards this value in the JVM still, and let's say I pass in the value equals 3, then it's true, and the result will be 3. That's pretty fast. Now, in case the value equals 0, then the whole thing is not true anymore. So that means the optimized code doesn't really work here. So, and then the compiler has to throw away the whole optimization and go again to interpretation C1, C2, and use then the whole clause, right? Because now suddenly both ways are possible. And that is de-optimization. And you can imagine that that really leads to some performance hits. Because once the code is already optimized and then you suddenly have to de-optimize, then it really is like a bam. Performance goes down because I have to interpret C1, C2 with all the method counter and so on. Okay, that's all great, right? But it takes time, of course. I told you all these steps we have to do before the code is really optimized. So that leads me to JVM startup. And unfortunately, I can't really see a lot of people because usually I ask who's suffering from JVM startup. And JVM startup, that's a little bit of a tricky definition. So I tried to come up with this chart where I say, first of all, we have the JVM startup. And I mean really the JVM itself, where we have to load the class libraries, we have to initialize it, we have to do some optimizations and all these kind of stuff. And that's usually pretty fast. You can test that on your own if you just create a program which has just one class and just hello world. Compile that and run that. It's awesomely fast because there's nothing to do. So that means the real startup time, when we talk about JVM startup, includes your application startup, right? This is the middle block that we see here. And there we have to load application classes, we have to initialize all the resources, we have to kick off application-specific logic, and we have to do the compilation, optimization, and so on. So that takes longer. That's usually the time to first response of the application. And in the lower part, you see this arrow, the first one. That's what we generally refer to as JVM startup, right? Because this is really tricky. I posted once something on Twitter, and then someone directly said, I don't understand. A JVM is super fast when it starts up. Yes, of course it is. But usually people talk about JVM startup, including application startup. And then you can even go a step further and say, we also have application warm-up. Because just think about it, if you have your application running, time to first response doesn't mean it's really warmed up yet. So you didn't really touch all pieces of the code, and the compiler didn't optimize everything. So that, again, could take some time. Sometimes people talk about JVM startup and they mean JVM warm-up, which means in literally application warm-up here, right? And this is usually optimizing. The JVM does only optimizing in that case. It does compile, decompile, and the application, usually you apply some workload to the application to warm it up. This is by high-frequency trading companies, they do that to warm up the stuff before they go online again. Okay. That leads me to this JVM performance graph that we once figured out, and you will find it on probably all the Azure slides because it's so useful. You see we have three parts here. The yellow one in the lower left corner, that's typically the interpretation phase. And you see it's really small. It doesn't really take that long. And then after that, we see the green area, which is usually the C1, compile and profiling phase. And then it goes into C2, and you see the performance grows and grows. This is level 2.1. And then usually this is what we define as a JVM startup, or time to first response. And then we see these gaps there. There's periodically these gaps. This is typically garbage collection pauses that we see in the performance. And then we see these gaps, and that's the optimization. It's when the compiler, let's say, warms up the code, it gets better and better, and suddenly something happens where, like a branch prediction, and it went in the wrong direction, right? The branch that was predicted was not the only one that happens, and suddenly the other branch happens, and then it has to de-optimize. And you see the performance gaps that you have then. You would like to avoid that if possible. If we now take this whole JVM startup thing into the microservice environment, then usually we would see something like that. We start the microservice the first time, JVM startup, second time, JVM startup, third time, JVM startup. Sucks, right? This is really, I asked that in the poll, and I will now ask who's suffering from JVM startup times here. Can you raise the hand? I see a few. Okay. Wouldn't it be great if we can do something like that? So we run the service once, and we have to start it up. And then the second time we run it, it's fast. Third time, fast. Always fast. That would be great. So let's take a look at some solutions that we have already and that have been mentioned by others in other sessions today. For example, class data sharing. This is, you have application or dynamic CDS, and this is part of the JDK. It's enabled by default since JDK 12 already, so you might use it without even knowing it. It dumps internal class representations into a file, and then this file will be shared among different JVM startups, so you don't have to do it all the time. You don't have to search the disk for stuff. It's already optimized there. And you can tune it. It's not just enabling, but there are also ways to tune it. There's a specific session just about app CDS. There's also, this is totally unrelated to optimization or hotspot detection because that happens before. It reduces class loading time, right? But that can reduce the startup time up to 2 seconds, sometimes even more. It really depends. But I saw stuff where it really, just by enabling it and tuning it correctly, the application starts up 2 seconds faster than before. And 2 seconds it's a lot. And it happens here. So at the class loading, right? It's not the compiling and all that comes after that. Okay. Then there's this other thing, ahead of time compilation. This is not new. In principle, it's quite old. But now, in the last years, I would like to say, suddenly everybody's like, hey, AOT. So that means no interpreting bytecodes, no analysis of hotspots, no runtime compilation of code. You start at full speed straight away, and GraalVM native image does that. Okay, so problem solved. That's it. You can go. Then I'm done. Yeah, should all use GraalVM native image? Well, not so fast. AOT is by definition static, and code is compiled before it is run. Right? So the compiler has no knowledge of how the code actually will run later on. And there's something that can help, which is the so-called profile-guided optimization, which works like, I can just tell you how it works in GraalVM. It's like they run it with the JIT, create a profile, take the profile and apply it when they create the native image. Means if you run the stuff and you run it long enough, then you probably have a huge profile. You can apply it to the native image, and then it will be probably quite fast. The problem is then it's still static. If something happens when the code is running, the code won't really adjust to that situation if there are changes. It will stay like this. And usually this is not hard numbers because it's hard to tell, but if we take a look at the JVM performance graph, then usually you can say the AOT compiled code without any PGO can reach up to 60–70% of the performance that the JIT can do. It can be more, it can be less. It really depends. And if you use PGO, you can reach up to maybe 90%. Sometimes you can hit the 100%, but usually you say the JIT is faster. And it's more flexible, that's for sure. Okay. And you need to create the profile, of course. So this doesn't come for free. And as far as I know, if you use GraalVM, the community edition, then you can't use PGO. It's only in the enterprise edition as far as I remember. Okay, so if we do shortly a comparison between these two, then we have limited use of method inlining with the AOT approach because we can only do that up front. The JIT can do that all the time. In the JIT, we have something like ongoing PGO, right? And we have no runtime bytecode generation in AOT, where the JIT can do runtime bytecode generation. Reflection is possible in GraalVM. It's hard, but it works. Reflection in JIT is not a problem at all. You can't really do speculative optimizations where the JIT can do that. So I could dig into that, but we don't have the time for this. You just have to believe. Overall performance will typically be lower with AOT than with the JIT. But the biggest thing is, for me at least, if you create a native image, then your runtime environment is different from the development environment. That leads to strange effects. So at one conference, someone approached me after the session and said they have a problem when they use GraalVM, for example. They compile everything, or let's say they put it in their CI/CD system, run all the tests, everything's green, they compile the native image, run it in production, and it crashes. And they have no idea why. The difference here is that native code behaves differently than JIT code. It's not the same. And that makes debugging not easy. So I think there are ways in IntelliJ at the moment, or they are coming, to make that more easy. But still, this is something that I don't really like with this approach. On the other side, you get full speed from the start, where the JIT needs to warm up. And we have no overhead because we don't have to compile at runtime, where the JIT has to compile all the time, right, more or less. And the memory footprint is smaller, that's for sure, because in a native image, we just compile the stuff that we need. Also means the AOT approach needs to know everything, the whole world. Otherwise, it won't work. Where the JIT, don't need to know. You can at runtime load stuff, and it will work. Okay. This is something I found on the web. It's just the same that I told you already. The reduced max latency here is related to the garbage collection because this is different in GraalVM. And this is a chart from a GraalVM guy. But I thought it's quite interesting to see. And in principle, it shows that the peak throughput is higher, but therefore startup speed for AOT is faster, low memory footprint, and so on. I already told you that. Okay, let's take a look at a different approach. And this is based on a project called CRaC, which is Checkpoint Restore in User Space. And that's a Linux project. And it's not that new. It is already part of the kernel since 2013. And it was made to freeze a running application or container and then checkpoint the state of this container to the disk and later on restore this application or container from the saved state back into memory. That's the main idea of this project. And it's already used or implemented in OpenVZ, in Linux containers, Docker, Podman. They all make use of CRaC or can make use of it. So you might have used it without even knowing it. The idea, just shortly, checkpoint restore, everybody of you that has a notebook or a laptop, when you close the lid and it's running, then it's exactly what's happening. The operating system creates some kind of a checkpoint. When you open it up again, it will restore from the checkpoint. We're talking about this process, right? Okay, it's mainly implemented in user space. The main goal, like I already mentioned, migration of containers for microservices. It heavily relies on the proc file system. This is only available on Linux, and not even all Linux systems run with proc. And that also means it is not available on Windows and Mac. Right? And I don't really see it there right now. But okay, we have it on Linux, and usually I ask the people who's running Java applications on a Windows server in production. Sounds funny, right? But no, there are people that do that. I learned that the hard way because I was trying to make a joke and then two people raised their fingers and I was like, oh, shoot. Okay. It can checkpoint the following things. So it can checkpoint process and threads, application memory, memory map files, shared memory, open files, FIFOs, pipes, sockets, inter-process communication channels, timers and signals, and it can re-establish a TCP connection from one side. So there's no handshaking or something needed, which is quite interesting. Okay, and of course, this comes without challenges. You can imagine if you create this checkpoint on one machine, and then you would try to restore it on another machine, will probably not work easily, because there might be open files that you rely on that are not available on the other system, shared memory, or you name it, right? There could be totally different things, environment variables that are not set. All this stuff is possible. Also, you can't really start the same instance multiple times on one machine. Not if you just use it on Linux. If you run it in a container, yes, that works, but not really, because the PID, the unique process ID, is also part of this snapshot. So that means if you would like to restore it, it's already there, it won't work. And yes, you are right if you guess, oh, wait a minute, so if I like to restore it and another process has the same ID, it will fail. Yes, that's true, it will fail. But we are working on a solution for that. So, for a Java virtual machine, it's even different, because if you run the Java virtual machine on Linux, it is an application, you would think, right? I can just snapshot it or checkpoint it and then restore it. Well, yeah, that's true, but just keep in mind that in this application, you run your application, and your application has no idea that it is checkpointed, right? So that means you have files open, you have a database connection or something, and suddenly everything's shut down. Fine. You restore it, the JVM will start, the application will start, will try to connect to the database, and then bam, oh, no database. Oh, file is not open, and then it will crash. Right? So it's not that easy. Okay, that leads me to CRaC. It sounds cool, but it's just coordinated restore checkpoint here. And the main thing is the coordinated. So Creo, this project, this library, comes bundled with the JDK to make sure that we always have the same. The heap is cleaned and compacted, right? So the JVM is in a safe state before we create the checkpoint. And it throws checkpoint exceptions, means if you forget to, let's say, close a file, it will tell you. This didn't work because there was still a resource open in a file. And it comes with a pretty simple API. We will take a look at that in a minute. It creates checkpoints using either code or JCommand. Okay. And it uses JVM save point mechanism. That's in principle the same that is used for the stop the world garbage collection to stop the JVM. And yes, the JVM will be stopped. It won't continue running. Because the first time I heard that, I was like, oh, that's so cool. I can create an application, and then I put in a trigger where I can create snapshots. And if something went wrong, I can just do undo and restore from the checkpoint. No, unfortunately not. So it will stop the JVM. It also means you can create or should create the checkpoint once, and then you deploy that, and then you run it. But we come to that. The whole thing is an OpenJDK project. So this is nothing that is only done. We do it by Azul, but we provide that to OpenJDK. Means if you go to openjdk.org/projects/CRaC, you will find it. And you can also download a JDK version there. And this is an Oracle OpenJDK. This is just the standard one. So I already mentioned that the application somehow needs to know when it gets checkpointed. That means CRaC does that. You run an application, before the checkpoint is triggered, we will tell the application, here, attention, you will get checkpointed, to give you as a developer the chance to do something like close resources or stuff. The same when we restore, we let the application know that it got restored, so that you have the chance to re-establish connections, for example, to avoid these problems that I mentioned before. Okay, if we start it, we have two parameters here. The one is -XX:, CRaC checkpoint 2 equals path, and then -jar, and then you start your jar. And this path is the path where the checkpoint files will be stored. So we pass that to the JVM so that it knows in case there is a checkpoint, I store the files in this path. And if you would like to restore it, you just call java -XX:, restore from equals path. CRaC restore from equals path. And then you point it to the path, and then it will start from that checkpoint. That's the main idea. Okay, the API, pretty simple. One interface, it's called resource, has two methods, before checkpoint, after restore. Pretty simple. And you have to implement this interface in all the classes that use resources. That sounds like a lot. but most of the times it's not. Usually it's like database connections, you have a database manager. Usually you have always a central point where you address these things, and in these classes you have to implement this interface, and then you have the two methods, before checkpoint, after restore, where you can, in the before checkpoint, you close the resources, like open files or stuff. In the after restore, you restore these connections, for example, or reopen the files. So, of course, somehow the JVM has to know which classes you have to trigger, right? And for that, you have to register these resources to the so-called context. And that you can get by the core.getGlobalContext method. It's a static call. You can just, every resource register itself in this core context. And then it looks in principle like that. So your class implements the interface, then you get the global context, and then you call on the context register resource. So this is the way it works. Pretty simple. And then what happens is that the context maintains a list of all the resources. And once you call you have a checkpoint, all the before checkpoint methods will be called, but they will be called in the reverse order you registered them. And that makes sense, because if you have, for example, resources that rely on each other, let's say you have the database connection first. The next resource, for what reason ever, needs the database connection. So you have to make sure that when you close it, first you close the second one, and then you close the first one. And when you do the restore, then in principle it's the same order that we had when we register them. So you decide the order you would like to register the resources, and then keep them in order is done by the context. Okay, you can also create the checkpoint, and the method name is a little bit misleading. It's not checkpointing and restoring, it's really just the checkpoint. By code, some people ask why. There are use cases, I don't want to dig into that yet, but there could be a reason when you have code that applies a specific workload to warm up something, then you can do that, and after you're finished, you can create the checkpoint, right? And you can even check if the checkpoint files are available, and if they are already in the folder, then you just don't do it. So there is a reason for that. Or you can use the J command to create the checkpoint. And now that leads me to a pretty simple example that should give you an idea. So if we have a program and there's a scheduled thread, every 5 seconds it will call into a loop, and in this loop it goes from 1 to 100,000 and creates random numbers between 1 and 100,000. And then it takes the number and calls is prime and checks if this number is a prime. But before it really calculates it, it checks if this result, true or false, for this number is maybe already in the cache. So it checks the cache. If the result is there, returns the result, which is pretty fast because this is just memory. If not, we have to calculate. And if you have, for example, a huge number, then that takes some time, okay? We get the result, we store it in the cache, and then we return it. It's slower. To make it a little bit more realistic, the cache not keeps the stuff forever, but it has a timeout. It starts after 50 seconds, and then every 10 seconds, it will check if a value is older than 10 seconds and will wipe it out. This just to make it more realistic. So that means the first run will be pretty slow because the cache is empty. Every number has to be calculated and put into the cache. And then over time, with each iteration, it should be faster and faster, right? And at some point, because I told you the cache will delete stuff after 10 seconds if the values are older, so it will get in some kind of a pattern, right? So the performance will be more or less stable. And I did some results on another machine, and then it was like this. So after 9 iterations, then it starts like, okay, now we get into this mode where everything is settled. All right, so I do a demo. I do a demo first in slides, and then I will show you the same stuff in reality, because here I can explain it. So first of all, I start the jar file with a command, and I point it to the CRaC-files folder. And then I start it. You see, I put some system out print lines there to show you the order I registered the resources. So I first register the generic cache and then the main. And then the first run was really slow. This is because it runs in a virtual machine here, so it took 27 seconds for the first iteration. And then the second one, 10 seconds, 4 seconds, and so on, and faster and faster over time. And then when we reach, for example, 17 milliseconds, I go to a second shell window and then execute J command, and I call it with the jar file. You can also use the PID, doesn't matter. So we see the PID on the left side. I could also use the PID, but I use the jar here and create the checkpoint. And then on the other side, this will happen. It will call the methods in the reverse order, like mentioned, and then it will create the checkpoint, and then it will kill the JVM. Some people ask, why does it kill the JVM? Because it really shuts down the whole stuff and stops it, get rid of all the resources. You can't simply just restart it. There are ways, I think in the OpenJ9 implementation, they have something like continue running. We don't have, so we can't. That means the thing is now stopped, and the files are somewhere on my hard drive in this CRaC files folder. Now I wait a little bit, and this is usually what we said, JVM startup. In this case, in reality, it's JVM warm up here, right? Because what I really did, I warmed up the cache in my application. But you can apply the same principle for JVM startup. And now if I do a restore, by calling Java minus and then the same stuff that I told you, CRaC restore from, I point it to the CRaC files folder, then we see this. We see that the resources will be registered in this after restored method in the order we originally registered them. And it's directly fast and continues counting. The question is, how does it work? Because I told you that after 10 seconds, the cache should be cleaned. So now I waited for more than 10 seconds. Usually the first time I hit the cache, it should realize, wait a minute, everything is outdated, and wipe the whole cache out. Well, and this is exactly the problem with this approach. So if you have time-dependent data, then you have to take care about it. What I did here, in the before checkpoint method, I stored the current epoch milliseconds in a variable. When I restore it, I calculate the delta between the stored value and the actual epoch milliseconds and applied the delta to all values in the cache. And that I did in the after restore method. And with this, I could make sure that all the values in the cache are still valid. If I didn't do that, and this is tricky because if you just applied it to your application, then you might see that it's not starting that fast, and you ask yourself, how could that happen? The reason is probably you have somewhere time-dependent data or state, and you have to take care about that. That might be a little bit tricky. Okay, and then it continues running. You see the cache is directly there, and it works. All right, so I created the checkpoint with this command. Like I said, it doesn't have to be the jar, it could also be the PID. And, or I can also do it from code, like core checkpoint restore. And typically, what you do is you run the application in a Docker container, create the checkpoint in there, store the state of the Docker container, and then you can restore from there. But once you start from the stored checkpoint Docker container, it will just start up pretty fast. But we will see that, hopefully, if I have the time. The next question is when to checkpoint. That's a tricky question. So what we do, we use this parameter -XX:+ print compilation. That means it will print out all the compilations that the compiler is doing. That's terrible if you view it because it's like, it's scrolling all the time. But over time, you will see it gets slower and slower. So less compilations are done. That means the code is probably all compiled. So we reach this one performance state, right? So where it's really 100%. At that point, you can create a checkpoint. This is just an idea, right? So that's what we do when we play around with it. Okay, the demo code you can find here. The JDK you can find, I will show it, it's github/CRaC. And just if you would like to start with it and play around, that's the easiest way to do. So it's cool, right? I showed you a demo that I did, and running on an OpenJDK version that we've patched, and it worked. Cool, we are so cool. So the question is, how good is it really? Well, of course, we did tests with other frameworks like Spring Boot, Micronaut, Quarkus. We also did some XML transform. These are the time to first operation, and that's milliseconds. You see, Spring Boot around 3.9 milliseconds, Micronaut 1 second, Quarkus 980, and the other one 4.3 seconds. Using CRaC, it was this. And that's pretty fast, I guess. And you see, it's interesting that even Quarkus had 980 milliseconds and the XML transform was 4.3 seconds. Suddenly they are more or less in the same range now. The reason is we just rely on I/O here, right? It's the state is stored to the disk and we just restore it from there back into memory. Means disks are usually quite fast. So that means that this really just relies on I/O, plus if you have a lot of resources you have to restore, then that might also take some time. But usually if you create a database connection or something, it's also in a range of milliseconds here. Quarkus has already, as far as I know, there's a prototype that has support for CRaC. For Micronaut, there will be a plugin. I heard it will be available probably this week, the next coming week, where it supports CRaC. And the Spring Boot stuff, we patched it a little bit. So we used a patch Tomcat, and we just told Spring Boot to use this one as the embedded web server to make that work. This stuff is also available on GitHub, so if you don't believe me, just check it out, play around with it, you will see that's the real numbers. Okay, then I also have some charts about time to complete N operations with Spring Boot. You see the red one is OpenJDK, the blue one is the CRaC version. The CRaC was linear from the beginning, where the red one needed to warm up, right? So this is the startup time that we see here, and with Quarkus the same. So these two frameworks are already fast, but with this you can get even faster, right? Okay, the summary. CRaC is a way to pause and restore a JVM-based application. It doesn't require a closed world, as with the native image. The benefit is extremely fast time to full speed. It eliminates the need to hotspot identification, method compilation, recompile, de-optimization, because that's already done when we create the checkpoint at the right time. It improved throughput from the start, and CRaC is an OpenJDK project, and it can save infrastructure costs. We heard that already. Cloud costs is something that you have to keep in mind, and usually what you see when you have services running in the cloud, then usually you see the CPU utilization on the left and time on the bottom. You see this spike there. This is because this is the JVM startup time. It just takes some time where we need to interpret, compile, and at the same time run your application. And therefore you need a lot of CPU time or CPU power. So that means if you create the checkpoint here and start from there, you can save this startup time and the CPU overhead, because suddenly you don't really need these high performance nodes anymore, because they're really expensive. Okay, all the stuff can be found here, github.com/CRaC. You will find the JDK there, you will find all the demos there, you can play around with it. It's only available for Linux x64. So if you would like to play around like I do on my Mac, that's my old Mac, and I only use it because it has an x86 machine, so or x64, so I can run it in parallels. There's also a wiki page where you will find information about the CRaC project. And now I just would like to show you a little demo. All right, so what I did, I took my application, put it in a Docker container, and on the first start, I just start the Docker container here on the left without any optimization. Just let it run. And you see, yeah, now it started. And it takes some time, 27 seconds before the first iteration is done. And usually if you have something, this is your microservice, you run it in the cloud, and I'm waiting, I'm the customer, like, oh, 27 seconds later, hopefully. Still not there yet. Okay, cool. We have to wait, sorry. Ah, here we go. Yes, first run. Oh, but now it's not even warmed up yet. So, but at least I get a response. Next call will be faster. 10 seconds. Come on. Ah, now it's 4 seconds, and then it's the same that we saw before. You don't want to go that way, right? That's what people suffer from. AWS Lambdas, for example, it's something that they really suffer from the startup time of the JVM. Okay, so what I did, I created a checkpoint in the Docker container, and saved the state of that. And now I restore from that one. Aha, here we go. Directly there, cache is filled. And the good thing is I can start it again on another one. And again, it's fast. I hope that makes clear what you can do with that. And it's still a JVM. That means even if the application now would completely change in behavior, for what reason ever, the JIT could react on that because this is just a JVM. This is nothing statically compiled. The JVM doesn't really know that it was stopped and restored, except that we added these two method calls and let the JVM in the application know. So with this, I hope I'm on time, and I would like to thank you for attending. Thanks. Oh, and if there are questions, because we don't have enough time, if you use this VOA app.
There's no time, but you can find it afterwards to the party.
You can put in the questions there, and I will answer them because they will stay in that app, and I will try to answer all the questions. Might take a little bit, maybe not all today, but I will try to.
Also a small gift to get back home. It's an olive tree. You can replant it if you have a garden or if you have a balcony with a large.
I will definitely.
Thank you so much, Gerrit.
Thank you.